3.6. Operations on functions. So I'm going to be looking at the algebra functions. So let C be a member of a field. I'll define the sum of two functions. So let F be a function, G be a function. I'll define these operations pointwise. So let the rule for F plus G be as follows. F plus G at X is just F of X plus G of X, where the domain of F plus G is just the domain of F intersect the domain of G. Let C be a member of your field. Then I can define scalar multiplication as follows. A constant C times F has the times F, evaluate X, is just C times F of X. The domain of CF is just the domain of F. Define the zero function to just equal 0 for all X. Define the additive inverse of a function F as being the scalar multiple, -1 times F. We'll define the product of two functions to have the following rule. F times G at X is just F of X times G of X, where the domain of F times G is just the domain of F intersect domain of G. I'll define the function 1 as equaling 1 for all X. I'll define the multiplicative inverse of a rule, a function G, as having the following rule. 1 over G at X is equal to 1 over G of X, where the domain of 1 over G, take away the kernel of G, where, if you remember, the kernel of G is just a set G of X is equal to 0. I'll define F minus G as F plus the additive inverse of G. I'll define F divided by G as F times the multiplicative inverse of G, where just to be sure that it makes more sense, I'll say that the domain of F divided by G is the domain of F, intersect the domain of G, take away the kernel of G. Two functions F and G will be said to be equal if their domains are equal and F of X is equal to G of X for all X in the domain of, well, F or in the domain of G. They're both the same domains. So it turns out that these functions defined with these type of algebra on it actually give us what's called a vector space. So let me explicitly give you what a vector space is in this particular case. So let A, B, and C be in your field. Let F and G be functions. Then we have the closure property for vector addition. F plus G is a function. So if F is a function and G is a function, then F plus G is also a function. If C is a scalar and F is a function, then C times F is also a function. That's the closure property for scalar multiplication. F plus G is the same as G plus F. That's the commutative property for vector addition. F plus the quantity G plus H is the same as F plus G plus H. This is the associative property for vector addition. There exists some function, which we defined above, the zero function, such that F plus the additive identity is the original function F. And so this is the existence of an additive identity. There exists a one function such that 1 times F is equal to F. So this is the existence of a scalar identity. Well, the existence of the scalar multiplicative identity identified with the scalar identity. For all F, there exists minus F, such that F plus the additive inverse of F is the additive identity. And so this is the existence of a inverse for the vector addition. C times the quantity F plus G is the same as C times F plus C times G. This is the fact that scalar multiplication distributes over vector addition. Next, A plus B times F is the same as A times F plus B times F. So this is the distributive property stating that scalar multiplication distributes over scalar addition. Next, composition. Composition is just a fancy way of saying substitution. It is just substitution written in functional form. And so, suppose I have that G maps X to Z and F maps Z to Y. Then the function that maps X to Y, I'll denote that by F composed with G. So F, little circle, G. So F of G. So let me do that. So suppose G is a rule from the set X to the set Z, and F is a rule from the set Z to the set Y. So let G and F be rules. Then the rule defined by F composed with G, which maps X to Y. So F composed with G at X is defined as F evaluated at G of X. And so this is just F evaluated at G of X. And it has the domain is of F composed of G is just the set of all X's in the domain of G such that G of X is in the domain of F. This will define a function, F composed of G, from the set X to the set Y, and it is called the composition G. Okay. Please note F composed with G is not the same as G composed with F. The identity function. The identity function maps X to X. So the identity of X is equal to X for all X. So notice that F composed with the identity function is just the original F, and F composed with, and the identity composed with F is just F for any function F. Let me do some examples. On page 378, let me do problem number 20. Let f of x equal x squared minus 7 and g of x equals the square root of x. Find each function and its domain. Okay, so let's look at f minus g. This is just f of x minus g of x. And that is your answer. Next, I want to find its domain. So let's find the domain of this. Well, I can take any number and square it and subtract 7 from it. But I have a square root. So if I have a square root, well, I don't want to take square roots of negative numbers. And so I want that whatever is within the square root to be non-negative. And so the domain of f minus g is just a set of all x's greater than or equal to 0. The domain is just the closed interval from 0 to infinity. And that's your answer. Let me do next problem. Oops. Let me get some more room. Let's just bring this up here. So I want to find two functions, f and g, such that h of x can be expressed as the function indicated. Several answers are possible. Okay, so I want to write h as f plus g. So I could let f of x equal 3x squared and g of x equal 2x. Because then f plus g at x would just equal h of x. So these are two possible answers. Well, one possible answer. This is one possible answer for f and g. I could have said 3x squared minus 1 and 2x plus 1. Then when you added them, the ones would have canceled. So there's actually an infinite number of answers, but this is probably the typical answer that most people would think of. Let f of x equal 2x minus 5 and g of x equal 5x minus 2. Find each value. So f composed with g at x at negative 3. This is the same as f evaluated at g of negative 3. So first, let's look at g at -3. So wherever I have an x, I replace x by -3. And so -15 minus 2, 18. So I want to figure out f at -17 because I want to figure out f of g of -3. G of -3 was -17. So wherever I see an x, I replace x here by -17. Move this down a little bit. And so f of -17 is -34 minus 5, -39. And so f composed with g at -3 is -39. So notice, to evaluate f composed with g at -3, wherever I see an x in the formula for g, I replace x by -3 to get a -17. Then, wherever I see an x in f, I replace x by -17 to figure out my final answer. Okay, so I probably need another page. Let f of x equal radical x and g of x equal x plus 1. Determine the domain of each composite function, then find the composite function. Okay, so let's recall that the domain of g composed with f is the set of all x in the domain of f such that g of x, such that f of x, I wrote the wrong thing, such that f of x is in the domain of g. Okay. So find the domain of f. So first I have to find the domain of f. Well, f is the square root of x, so I want x here to be greater than 0. So the domain of x is the set of all x's greater than or equal to 0. Let's find the domain of g. Well, the domain of g is everything. All you're doing is just adding 1. So the domain of g is just everything. So I want to find, so the domain of g composed with f will be, well, every x in the domain of f. And so that's every x greater than or equal to 0, such that f at that x, the square root of x, is in the domain of G. Well, everything's in the domain of G. And so we just have to have that x is greater than or equal to 0. And so the domain is the closed interval 0 to infinity. It says to now determine G composed of F. So now let's determine what the rule is, then find the composite function. So what is G composed with F? So G composed with F at X. Wherever you see an X in the formula for F, well, wherever you see, let's state it this way. So you'll just evaluate F of X. So wherever you see an X in the formula for G, replace X by the function found by F of X. So wherever you see an X in the formula for G, replace X by the formula given by F radical X. So wherever you see an X in G, replace X by the square root of X. And so I'm going to replace X here by the square root of X. And that is my rule. And given the domain, notice that if you would have plugged in a negative number for X, you would have gotten an answer that would not be real. Let me do from 58. Well, we already know what the domain of G is. Is all real numbers. Therefore, the domain of G composed with G, which is the set of all x's in the domain of G, is in the domain of G. Well, every x is in the domain of G. G of x is just x plus 1, which is certainly in the domain of G because everything is in the domain of G. And so this is everything. So the domain of G composed with G is all real numbers. Now let's determine the rule for G composed with G. So G composed with G at X is found by replacing every X in the formula for G by the formula given by G of X. So I'm going to replace every X in this formula for G by X plus 1. So wherever I see an X here, replace X by X plus 1. And so this is equal to X plus 1 plus 1. And so G composed with G at X has the rule X plus 2. Let me do problem 64. Let f of x equal 1 over x minus 1 and g of x equal 1 over x minus 2. Determine the domain of each composite function, then find the composite function. So let's do that. So let's find the domain of f. Well, I don't want to divide by 0, so it's the set of all x's not equal to 1. Let's find the domain of G. So the domain of G well, again, it's 1 over x minus 2. So again, I don't want to divide by 0. So setting x minus 2 to 0, I get x equal 2. So it's a set of all x's not equal to 2. So now let's find the domain of, what is it? G composed with F. Of G composed with F. So the domain of G composed with F is the set of all x's in the domain of F such that f of x is in the domain of G. Okay. So well, the domain of F is all numbers not equal to 1. So it's all numbers not equal to 1 such that maybe I'll just actually such that f of x is in the domain of G, but the domain of G is everything that's not equal to 2. Okay. And so this is the set of all x not equal to 1 such that f of x, which is 1 over x minus 1, is not equal to 2. Oh, okay. So let's do this. Let's set this equal to 2 and see what x is equal to. So let's look at 1 over x minus 1. Let's find when this is equal to 2. So let's multiply by x minus 1. So I get 1 is equal to 2x minus 2. Add 1 to both sides. So 2x is equal to 3. So x is equal to 3 halves. Hmm. Oh, I see. Okay. Okay, so I want x not equal to 1 and not x not equal to 3 halves. So the domain of, now I forgot, G composed with F, right? G composed with F is a set of all x's not equal to 1 nor 3 halves. And so this is equal to negative infinity to 1 union, union 1 to 3 halves, union 3 halves to infinity. So that is the domain of my function. Let's actually determine the function. So now let's find this composite function, g composed with f. So g, so let's determine the rule for g composed with f. So g composed with f at x is equal to. So wherever I see an x in g, I'm going to replace x by the rule given an x in g here. Wherever I see an x in g, I'm going to replace x by 1 over x minus 1. So wherever I see an x here, I'm going to replace x by 1 over x minus 1. And so wherever I see an x, I'm going to replace x by 1 over x minus 1. Okay, so let me simplify this. So let me multiply by x minus 1 and by x minus 1. So this becomes x minus 1 over, the x minus 1's cancel, 1 minus, multiply a negative 2 inside the parentheses. So it's a negative 2x. And so g composed with f at x is equal to x minus 1 divided, okay, come on, x minus 1, trying to get the screen back. It's equal to x minus 1 divided by 3 minus 2x. But that's only if, so that's the rule. But that's only true if I also tell you the domain. Because notice that actually, if I plug in x equal 1 here, you'd actually get that this works. But this is only with the domain as follows. Domain of G composed with F. Everything except for 1 and 3/2. Okay. Just trying to write, that's all. Union 3/2 to infinity. So this is my function, the rule for my function, but only on this domain. So